Section 5.3 is exponential functions. In this section, we're going to be looking at what an exponential function is and talk about exponential growth and decay, as well as calculating compound interest. A linear function adds a fixed amount to the previous value of y for each unit increase in x. For example, if we have f of x equals 10,000 plus 500x, 500 is added to y for each increase of 1 unit in x. An exponential function multiplies a fixed amount by the previous value of y for each unit increase in x. For example, in f of x equals 10,000 times 1.05 raised to a power of x, y is multiplied by 1.05 for each increase of 1 unit in x. An exponential function can be represented by f of x equals c a to the x, where the base of this function is a, and that base has to be non-negative and cannot be equal to 1, and c is greater than 0. This is an exponential function with base a and coefficient c. If you'll notice here on the exponential function y equals 2 to the x, for each single unit increase in x, we multiply the previous y value by 2 to get the next y value. But with a linear function, for each unit increase in x, when we have the function y equals 2x, we add 2 to get to the next y value. An exponential function starts growing rapidly, but a linear function forms a straight line. In example 1, we're asked to determine whether we have a linear or an exponential function that models the data. If you'll notice here in part A, we're increasing x's by 1 unit each time. And as we go from the first value of y, we're subtracting 3 each time in order to get to the next y value. Because we subtract 3, this would be a linear function. In part B, for each unit increase in x, it looks like I'm going to be multiplying the previous y by 3. So here, 2 times 3 is 6, and 6 times 3 is 18. So this would be an exponential function. So A, we have a linear function, and B, we have an exponential function. Whenever we have an exponential function where the base is bigger than 1, we have what's called exponential growth, and it grows by a factor of a. The y-intercept will always be whatever c is. So for example, your y-intercept will be 0c. Remember, to find the y-intercept, we plug in a 0 in place of x and solve for y. As long as the base is bigger than 1, this function will always be increasing, and we will always have an horizontal asymptote at the x-axis. If we have a base that's between 0 and 1, if we're raising a base to a power of x that's between 0 and 1, we have a decreasing function. The y-intercept stays the same and the horizontal asymptote stays the same. We just switch our function from increasing to decreasing if the base is in between 0 and 1. The larger the base is, the steeper the curve will be. So here's a graph of a function y equals 1.3 to the x, and notice it's increasing because the base is bigger than 1. The y-intercept is going to be at 0, 1, because when we plug in a 0 in place of x, we get 1 for y. Anything raised to a power of 0 is 1. If we increase that base to 1.7, you see how this graph still passes through the same y-intercept, but it gets steeper faster. And if we increase our base to 2.5, it gets steeper even faster. As long as the base is bigger than 1, you'll have an increasing function with a y-intercept at 0, 1 and a horizontal asymptote at the line y equals 0, or the x-axis. The minute that we switch to a base between 0 and 1, we have a decreasing function. Notice the y-intercept stays the same for all of these graphs, and the smaller that base is, the closer it is to 0, the steeper this curve is, the more rapidly it decreases until it approaches our horizontal asymptote of the x-axis. Some properties of exponential functions. An exponential function f is defined by the function f of x equals c a to the x, where a is greater than 0 and not equal to 1, and c is a constant that's greater than 0. If you have an exponential function, it will have the following properties. The domain of an exponential function will always be all real numbers, and the range will always be from 0 to infinity. The reason the domain is all real numbers is because you can raise a number to any power that you want. And this will always be a positive value because you're multiplying a positive value times another positive value. So that's why the range goes from 0 to infinity. The graph of f is continuous with no breaks. The x-axis is a horizontal asymptote. There's no x-intercepts, and the y-intercept will always be at the point 0, c, whatever c happens to be. If the base is bigger than 1, the function is increasing over its domain, which is all real numbers, and if the base is between 0 and 1, the function is decreasing. This function, if you'll notice, is also a one-to-one function, and therefore that means it has an inverse. In the next section, we'll see what the inverse of an exponential function is. In example 2, we're told to let f of x be equal to 4 times 1/5 to a power of x, and then we're asked to complete parts a through e below. So what would be the domain and the range of this function? Recall, the domain of any exponential function will be all real numbers, so it'll be the interval that goes from -infinity to infinity. Because there's no vertical shift here, the range will also be from 0 to infinity. There's no power that you can raise a positive number to and have that value be negative. That's why our range is all positive values from 0 to infinity. Part B asks, is f either increasing or decreasing over this domain? Well, if you notice here, this base is between 0 and 1, therefore this will be a decreasing function. And it's a decreasing function because the base of the exponent is between 0 and 1. On Part C, we're asked to find any asymptotes of the graph of f. Well, exponential functions, unless there's a vertical shift, will always have a horizontal asymptote at the x-axis. The equation for the horizontal asymptote is y equals 0. This is also known as the x-axis. Part D asks us to find any x or y intercepts on the graph of f. Remember, in order to find your x-intercepts, you want to let y be equal to 0 and solve for x. Well, there's no way that a positive number raised to a power times another positive number will ever be equal to 0, so we have no x-intercepts here. And to find our y-intercept, we replace x with 0 and solve for x. Well, anything raised to a power of 0 is equal to 1, and 1 times 4 would be 4. Therefore, we have a y-intercept at the point 0, 4. If you want to see how I got that value, how I got it was I took my equation y equals 4 times 1/5 raised to a power of x, and I plugged in a 0 in place of x and solved for y. Well, anything raised to a power of 0 is 1, and that gave me 4 times 1, and 4 times 1 is 4, so my y-intercept is going to be at y equals 4, x equals 0. Is f a one-to-one function, and does it have an inverse? Remember, we learned that every one-to-one function has an inverse. If I were to graph y equals 4 times 1/5 raised to a power of x on my graphing calculator, I would see a graph that looks like this. Notice it's a decreasing function. The x-axis is the horizontal asymptote. Our y-intercept is at the point 0, 4, and it is a one-to-one function because the graph passes the horizontal line test. Because f is a one-to-one function, it has an inverse. In example 3, we're told to explain how to obtain the graph of g from the graph of f of x equals 2 to the x. Then graph both f and g in the same xy plane. In Part A, we're told that g is equal to 2 raised to the x minus 1. Well, remember, this is a horizontal shift because this constant occurs inside of our parent function, and horizontal shifts move opposite the sign, so this would be a horizontal shift to the left 1 unit. That means that I take this point and I move it to the left 1 unit, and then I can take this point and move it to the left 1 unit, and this point and move it to the left 1 unit, and then connect the dots and sketch in my curve for Part A. This would be the graph of g of x equals 2 raised to the x plus 1 power. For Part B, I'm asked to graph g of x equals -2 to the x. Well, this negative in front of a parent function reflects that function across the x-axis. So the graph of this would be the graph of my parent function, which is graphed here in red, f of x equals 2 to the x, and I just reflect it across the x-axis, and I can take these points at 1, +2, move it down to -2, at 2, +4, move that point down to -4, and then sketch in the graph so that it looks like this. And this would be the graph of g of x equals -2 raised to a power of x. So the transformations that we learned in previous chapters still apply to exponential functions. Next, we have the compound interest formula. If a principal of P dollars is deposited into an account paying an annual rate of interest R expressed in a decimal form, compounded or paid N times per year, then after T years the account will contain A dollars, where A is equal to the principal times the quantity 1 plus R divided by N raised to a power of NT. So if we're compounding annually, N is equal to 1. If we're compounding semi-annually, that means you're getting paid interest twice a year, and N would be equal to 2. If you're compounding quarterly, there's 4 quarters in a year, so N would be equal to 4. Monthly, N would be equal to 12 because there's 12 months in a year. Weekly, N would be equal to 52. And daily, N would be equal to 365 because there's 365 days in a year. This you need to know in order to use this formula. The principal P is the amount of money that you start with. R will be your interest rate written as a decimal, and N is the number of times you're compounding per year, and T is time measured in years. In example 4, we're told, suppose $1,000 is deposited by a 20-year-old worker in an individual retirement account that pays an annual interest rate of 12%. Describe the effect on the balance after 45 years at age 65 if interest were compounded quarterly rather than annually. In order to work this problem, we're going to use the compound interest formula, which is A equals P times 1 plus R over N raised to the NT. If we're compounding quarterly, N will be equal to 4. If we're compounding annually, N would be equal to 1. The principal for this problem is the $1,000 that you start your investment with. So if we're compounding quarterly, in order to find the amount of money I have at the end of 45 years, I take 1,000 times 1 plus the 12% divided by 4 raised to the 4 times 45. If I'm compounding annually, the amount of money that I have at the end of 45 years could be found by taking 1,000 times 1 plus 0.12 divided by 1 raised to the 1 times 45. If I clean these formulas up, I end up with A equals 1,000 times 1 plus 0.12 divided by 4 is 0.03, so that's going to be 1.03 raised to the 45 times 4 is 180. And over here I get A is equal to 1,000 times 1.12 raised to the 45. Now I'm going to go to my calculator to find out what these dollar amounts are. So for the first problem, I have $1,000 times 1.03 raised to the 180. And then for the second one, I have $1,000 times 1.12 raised to the 45. So it looks like if I'm compounding the same amount of money quarterly, I end up with $204,503.36. And if I'm just compounding my money or my investment annually, I end up with $163,987.60. So what does that compounding quarterly benefit me? Well, to answer that, I would subtract these two numbers. So it looks like by finding an investment that compounds quarterly as opposed to annually, I earned an extra $40,515.76 on my $1,000 investment. The more often you compound, especially over time, the better off you are in the long run. Another type of compounding we have is continuous compounding. Compounding that is done more frequently by letting n become large without bound is called compounding continuously. The exponential expression 1 plus 1 over n raised to the n reaches a limit of approximately 2.718281828 as n approaches infinity. This number happens to be what we call Euler's number. This value is so important in mathematics that it's been given its own symbol, e, sometimes called Euler's number. The number e has many of the same characteristics as pi. It's a transcendental number. It's a decimal expansion that never terminates or repeats in a pattern. It's an irrational number. The natural exponential function is given by f of x equals e to the x, where e is approximately 2.71828. When we compound continuously, if a principal of P dollars is deposited into an account paying an annual rate of interest R expressed in decimal form, compounded continuously, then after T years the account will contain A dollars, where A is equal to P e raised to a power of RT. Once again, your R has to be written as a decimal. In example 5, we're told that the principal in an IRA is $1,000 and the interest rate is 12%, compounded continuously. How much money will there be after 45 years? Now we use the formula for compounding continuously. You have to explicitly be told that you're compounding continuously if you're going to use this formula. So for this problem, our principal was $1,000, and then we have e raised to the 0.12 times t, where t is equal to 45 years. Notice the interest rates are the same as what we had on the previous problem, so now we'll see how much money we could have gained if we had compounded continuously. To put the e in your calculator, you hit second ln, and then that gives us the e for our base, and our exponent's going to be 0.12 times 45. So by compounding continuously, we end up with $221,406.42. By compounding continuously, we end up with $221,406.42. That's still more than what we got whenever we compounded quarterly. So like I said, the more often you can compound your investment, the more money you'll make in the long run. If we get out of the realm of finance and we start talking about natural exponential growth and decay, if a sub naught is the initial amount of a quantity a at time t equals 0 and k is positive, then we have exponential growth here because our exponent is positive. But if our exponent is negative, we have exponential decay. So this graph represents exponential growth, where our initial amount is a sub naught. This graph represents exponential decay because we have a negative in the exponent, and a sub naught is the initial amount that we started with. For this problem, you have to be told what k is equal to, and t does not necessarily have to be time measured in years like it does on the finance problems. In example 6, we're told that sometimes after a patient takes a drug, the amount of medication A in the bloodstream can be modeled by the formula A equals a sub naught e to the negative RT. This is exponential decay, where a sub naught is the initial concentration in milligrams per liter, r is the hourly percentage decrease in decimal form of the drug in the bloodstream, and t is the elapsed time in hours. Suppose that the drug's concentration is initially 2 milligrams per liter and the r is equal to 0.2. Part A says find the drug concentration after 3.5 hours. The first thing we want to do is set up a formula that we'll use, and that formula is A equals, we need our initial amount, and for this we're told that our initial amount was 2 milligrams, e raised to the negative 0.2 because r we were told is 0.2 t. This is the formula that we use. To answer the question in part A, we're asked how much drug is left in the bloodstream after 3.5 hours. In order to solve this, or to find this answer, we just need to plug in a 3.5 in place of t. Now we go to our calculators. In our calculators, we type in 2, second ln will give us the e, and then we have a negative, and be sure you use the negative button, not the subtraction sign. We have a negative 0.2 times 3.5, and we see that we have 0.9932 milligrams per liter. Part B asks, when did the drug concentration reach 1.5 milligrams per liter? In order to answer Part B, we're going to use our graphing calculators. What I'm going to do is I'm going to type in this function that I have written in red. We have 2 second ln negative 0.2, make sure you use the negative, and then x is going to be our variable for our graph. And I want to know where this function is equal to 1.5 milligrams. And I'm going to hit zoom 6 to get a standard window and see the graph. So here is the graph of the function a equals 2 e to the negative 0.2 t, and now we have the function coming in y equals 1.5. To answer the question in part B, I'm just going to zoom in and find this point of intersection. The way I do this on my calculator is I'm going to hit second calc, which is right above the trace button, and I want the point of intersection, so I hit number 5. And I use these arrows here to move the cursor over close to the point of intersection, hit enter to select the first function, hit enter to select the second function, then it offers a guess, but I don't want the guess, I want the exact value, and this is the x value that gives me my exact value. Remember, x in this function represented the time measured in hours. The y value here represented the concentration of the drug. What that means is that in approximately 1.4 hours, the drug concentration, the y value here, will be 1.5 milligrams per liter. And this wraps up section 5.3.